So in this next section, we're going to be solving linear systems. So this is where we have several linear equations and we want them to simultaneously be satisfied. Now, if you're talking about two lines, they will be simultaneously satisfied where they intersect. So one way that you can solve a system is you can graph it and figure out the intersection point if there is one. So let's solve this system here by graphing both equations on the same set of axes and then reading the solution from the graph. In other words, that intersection point. Okay, so let's do that. So solution from the graph. Solution from the graph, i.e. the intersection point. Okay, so let's just graph each one separately. So in this one, we're going to have to put it into the y equals mx plus b form. So here we will subtract the 5x from both sides. And we have negative 2y is equal to negative 5x plus 10. And divide both sides by negative 2. And we have y is equal to 5 over 2x minus 5. So this is your m, and negative 5 is our b. So we can graph that. So b is negative 5, 1, 2, 3, 4, 5. So at negative 5. And the rise is 5, so positive 5, and the run is 2, and so we will go through this point. And so let's try our best to draw a straight line. Wow, that didn't look so perfect. It's kind of hard to do this. Okay, and 1, 2, 3, 4, 5 over 2, so we're going to go to this point next. Okay, so that continues on. And our second equation here, this one, we can do the same thing, solve for y. So we will subtract x, and we will have negative x minus 1, and we'll negate both sides to get x plus right, so all I'm just doing here is I'm going to negate both sides, right? So negatives all around. And so our m is 1, and here is our b. Our y-intercept is 1 here. Okay, and our slope is 1. So the rise is 1 versus the run of 1. So okay, and don't need to really do this part so much, but do you see the intersection point is right here? So where the red line and the blue line intersect, because I could use purple to designate that intersection point. Okay, so the intersection point is the solution to the system, and what is that? So the intersection point tells us is so 1, 2, 3, 4, 1, 2, 3, 4, 5. So that would be 4, 5. So that is x is equal to 4, y is equal to 5. But you can also just say that this is the solution. That's fine. That point. Okay. So 4. Whoops. Sometimes when I write the 4 like this, it somehow comes out to looking like a 9. 4, 5. Okay. So next, let's try to solve the exact same system using what's called the substitution method. So instead of solving this graphically, where we graph both equations and then we figure out the intersection point, what we can do is take our two equations that we had up above. We can solve for one of these variables in one equation and then substitute it into the other one. All right. Now, the choice is kind of arbitrary in which equation and which variable you pick initially. So I'm going to pick this bottom equation because it's sort of it's a little bit easier to sort of say what, for example, x is. You see that to say, like, if I take this second equation here, this second equation, okay, notice that if I just add y to both sides, then I have x is equal to -1 plus y, right? And now what I can do is I can now substitute x is equal to y minus, that's y minus 1, right? That's the same thing as y minus 1. Y minus 1 into equation 1. So if I call this equation 1 and this equation 2, what would I get? So if I replace x with y minus 1, then what happens? So then I have 5x minus 2y equals 10 becomes the following. It becomes 5 times y minus 1, right? Replacing the x with y minus 1 minus 2y is equal to 10. And you see, now I only have y. So this is actually going to tell us what y actually is. So distributing the 5 and simplifying. So 5 minus 2 is 3y minus 5 is equal to 10. And then I can add the 5 over here. And we have 3y is equal to, whoops, it should just say 5, not 15. So that's 15. And dividing by 3, we have y is equal to 5. Okay, and then now, using our substitution, x is equal to y minus 1. Is what? So substituting in our solution, we have 5 minus 1. So that is 4. So x is 4. And you see we get the exact same solution. So the solution is x is equal to 4 and y is equal to 5. Or you could write it in the point. You could write it as a coordinate 4, 5, just like we had up here. So it's the same exact solution. Okay. So again, the idea is solve for one of the variables using, first pick one of the equations, then solve for one of the variables and substitute it into the other equation, and you will have eliminated one of the variables. You see, by substituting in for x, we only had y's, and we could solve for it and then resubstitute back into this equation, and you get the other one. So that's called the substitution method. Okay, so let's solve another one. So solve the following system by graphing both equations and reading the solution from the graph, just like we did before. So this first one, let's figure out what the slope and intercept are. So 3x plus 2y equals 4. So subtract 3x from both sides. And 2y is equal to negative 3x plus 4. Dividing both sides by 2, we have y is equal to negative 3 halves x plus 4 over 2 is just 2. So our slope is negative 3 halves and our intercept is 2. So positive 2. So if this is 1 and this is 2, then here is our intercept. The slope is negative 3 over 2. So then the rise is negative. So 1, negative 1, negative 2, negative 3. The run is 2. Okay, and so our line will connect these points and continue. for the second one, let's switch to a different color and solve this. So we have 2y minus 3x is equal to 4. So 2y, if I add 3x to the other side, and now divide both sides by 2, we have y is equal to 3 halves x plus 2. So now, well, we have the y-intercept is at 2, so I think we can see where the intersection point is. So the rise is 3 and the run is 2. And it looks like the intersection point is right here at the y-intercept. So the solution is just going to be the 0, 2. So the solution is 0, 2, right? That's where the intersection is. 0, 2, or so you could either write that, or you could write x is equal to 0, y is equal to 2. Now let's solve the same system using what's called the elimination method. So the elimination method is you are going to take one of these equations and scale it so that we can eliminate one of the variables. And let me show you how this really works. Now, the first step is to align. We should really line up the variables. So step 1, let's align variables. Okay, so see how we have the x's are not above each other and the y's are not above each other. So let's just rewrite them. So the first equation, just leave that alone. But the second equation, we can write this as negative 3x plus 2y is equal to 4. Okay, now here is where we can eliminate a variable. So do you see that? Let's try to, so step 2, eliminate a variable. Do you see that the coefficient in front of the x for each of these two equations, they're just opposites. You see that this is 3x and this is negative 3x. So if I were to add these two equations together, right? So if I add these two equations, what do I actually get? Do you see that you'd have 3 minus 3 gives us 0x. So I have just eliminated x from this equation. See what happens. So 2 plus 2 is 4y, and 4 plus 4 is 8. So we end up with just 4y is equal to 8. Okay, so you see how we eliminated the x that way. So eliminating a variable, that's the general procedure. You're going to try to make the coefficient sort of the opposite of what it already is. So let's say that you wanted to eliminate y instead. You would just try to make one of these a negative. So you could multiply one of the equations through by a negative, and then you could add, and you would eliminate the y. But here, I already had the x's had opposite coefficient signs, so that was the easier one to eliminate. All right, and then now you're just left with this equation that only has y, and so we can solve for y. And y would be 2. Okay, and how do we figure out what x is? Well, all you got to do is now substitute into one of the original equations. Remember that the solution is actually going to be a solution it's going to be on both of these lines. So if they do actually indeed intersect, it doesn't actually matter which one you substitute into. So let's substitute into the first one. So we have 3x plus 2 times 2, that's our y that we're substituting, equals 4. And then that would say 3x plus 4 is equal to 4. So subtracting, we have 3x is equal to 4 minus 4 is 0. So x is dividing both sides by 3. We have 0 over 3, which is 0. And so your solution is what? So solution, x equals 0, y equals 2, which is the same as above. Or you could write it as 0, 2, like this. And that's the same as our graphical solution. So now we're just going to continue using substitution and elimination methods and see if we can solve the following. So solve the following system using a substitution method. So remember, with substitution, you're going to have two equations. You solve for one of the variables and substitute it into the other one. Well, look at this, the second equation here. So if I call this equation 1 and equation 2, I already have y solved for. So why don't we just substitute this into equation 1? So substitute 2 into equation 1. So what would we get? We'd have x minus y equals negative 3 becomes the following. It becomes x minus y is equal to 3x plus 5 in the second equation, so we just replace that. And now distribute the negative. So that becomes negative 3x and negative 5. And combine. So these two combine to give us negative 2x. And we can add the 5 over here. So we will have negative 3 plus 5. So negative 2x is equal to positive 2. Dividing by negative 2, we have x is equal to negative 1. And then now, so y is equal to, so again, you could actually substitute this into either equation, but I already have y isolated, so maybe I should just substitute into this one. So 3 times negative 1 plus 5, so we have negative 3 plus 5. So y is equal to 2. So solution, x is equal to negative 1, y is equal to 2. Or you could write negative 1, 2 like this. So let's solve another one. So using substitution method, here we have equation 1 is 4x minus y equals 5, and the next one is 4x plus y equals 1. So one of the variables is not already isolated, so it doesn't matter which equation you start with, but let's solve for one of these variables. Now in this first equation, it looks like it's going to be easier to solve for y because the coefficient is not a 4. So let's solve for y. Again, that's arbitrary, but what do we have? 4x minus y is equal to 5. All I have to do is, couldn't I just bring the y over here and subtract 5? And so I'll have 4x equals 5 plus y minus 5 minus 5. Then I will have 4x minus 5 is equal to y. So here is my substituting equation, and now we'll sub into 2. Right there, right? Y is equal to this. So this becomes 4x plus y, this thing, 4x minus 5 is equal to 1, and so we have 8x minus 5 is equal to 1. So then 8x, adding 5 to this side. So 1 plus 5 is equal to 6. So we have 8x is equal to 6. So dividing both sides by 8, we get x is 6 over 8, which you can reduce. They have a common factor of 2 in them. So this reduces to 3 over 4, right? Dividing each of those by 2. And then finally, y would be equal to what? 4 times this minus 5. So that will reduce the 4. So we have 3 minus 5. So y is just minus 2. So that's going to give us our solution. Maybe we'll write that up here. Solution. 3/4 negative 2. Or you can write them separately. And let's solve this one using similar procedure. So we have 10x plus 2y equals negative 6, and y is equal to negative 5x. Oh, well, that's nice. Y is already solved for. So we kind of have a little bit of the work already done. So let's substitute this right into the equation 1. So sub 2 into 1 to get what? 10x plus 2 times negative 5x is equal to negative 6. So what does this give us? So we get 10x, and then minus 10x is equal to negative 6. So then this side becomes 0 equals negative 6. Well, that's strange, right? This is impossible. So what does that mean? Okay, well, we have two equations, and by themselves, they are linear equations, right? This would give us a line, right, if you wanted to graph it, and this would give us a line. Okay, so when you get that the system gives you something impossible, well, that just means that this system does not have a solution. So graphically, what that would mean is you have two lines that do not intersect one another. And what kinds of lines are those? Well, first of all, let's just say there's no solution. Okay, so when you get to a point where you get an impossible equation, that just means that there's no solution. Okay, but let's sort of think about this geometrically. What kinds of lines do not intersect? What do they have to look like? Well, they would actually be parallel lines, right? And let's see if that is something that kind of makes sense. What is the slope of this? The slope is negative 5, right? If you calculate the slope of the first equation here, what would you get? Well, you'd bring over the 10 as negative 10x, and then you divide by 2. So that slope would also be negative 5. So you see that the slopes are actually the same. So these two lines are actually parallel, right? These two lines that I drew have positive slope. But, if you want an illustration, if they were going to have negative 5, they're still going to be parallel. That's the important thing. They would more look like this, right? So, negative 5 and negative 5. Okay. So they're going to be parallel lines, actually. Okay. So it geometrically kind of makes sense that you could have two equations that just don't happen to intersect, and that's why you're getting sort of this impossible situation. Okay, now let's try to solve a system, again, using elimination method. So the procedure here is usually, well, look at the coefficients. So they're already lined up, right? The x's are lined up, the y's are lined up, constants are lined up. It's already kind of nice and organized, but look at the coefficients. So the coefficients are 1 and 2 for the x's, and negative 1 and positive 1. So do you see that it makes sense to eliminate the y here because they're already opposite, not only in sign, but they're actually just opposite in what they are, negative 1 and 1. So what I'm going to do is I'm going to add these two equations right now. I don't actually need to do anything, and we're going to eliminate the y by doing that. So x plus 2x is 3x. The y's are gone because that's going to give us 0y. and then this will be 12, and then divide both sides by 3, and so we have x is equal to 4. So y, if you substitute this into the first one, we'll have 4 minus y is equal to 4. So then adding y over and subtracting the 4, we have y is 0. So that's our solution. So the solution is 4, 0. So sometimes the elimination method can be quite quick, right, instead of substituting. Yeah. So in a lot of situations, I'll just give you the option. It's just good to see both, because sometimes one can be a little bit quicker than the other, and it's very this type of technique comes up in other situations, so it's good to see both of them. So one thing I'd like to show you is how to actually solve this problem another way. So in this, the way that we just solved it was we eliminated the y variable, but I kind of want to show you that that choice is actually arbitrary. I'm going to do the same thing again, so I'm going to solve it a second way, and let's try to eliminate the x variable instead. All right, now you can do that, but the strategy usually is to look at the coefficients and see which one you have to do the least amount of work. I'm going to have to definitely do more work because these coefficients are not the same, but negatives of each other. So what could I do here? I could take this first equation and I could try to make the coefficient in front of x -2. So what we're going to do is we're going to multiply this first equation by -2. And if we do that, then we will get a coefficient that is the negative of the coefficient of x in the second equation. So if we multiply the first equation by -2, whoops. What do we get? We get -2x, and then distributing this negative in, right, we'll have positive 2y is equal to -8. And then rewriting equation 2, so now this is like equation 1 again, but just modified. So I put a little star there. In equation 2, we have 2x plus y is equal to 8. So the reason that I'm showing you this is in some situations there might not be an obvious optimal choice, but this is the type of thing that you would actually have to do. Okay, so now if we add these two equations, we will eliminate the x variable. You see that? Because -2 plus 2 is 0, and then we'll have 2y plus y is 3y, and -8 plus 8 is 0. And dividing by 3, we have y is equal to 0, which matches what we had before. But let's substitute that in, and now we have x minus 0 is equal to 4. So x is equal to 4. So see, even though that we took sort of a less optimal route, it actually took about the same amount of time. And we get the same solution. All right. The real reason that I wanted to show you this is just sometimes it might not already be obvious which one is the most optimal. And I wanted you to kind of see what you would have to do. You want to multiply one of the equations so that the coefficients in front of the variable you're trying to eliminate are negatives of one another. Okay? All right, so let's solve another one, and let's look at what we have. So we want to use the elimination method. We have 2x minus y equals -2, and -2x minus y is equal to 2. So what is the simplest variable to eliminate in this situation? Well, the x, because these are already they're already negatives of each other, right? So we don't have to do any multiplication to make them negatives of each other. If you wanted to eliminate y, we could multiply the second equation by a negative, but we don't have to do any of that. So I could just add them right now, and we get the x's are eliminated, and we have negative 2y is equal to 0. So then y is equal to 0. So now substituting this back into one of the equations up above, 2x minus 0 equals negative 2. So 2x is equal to negative 2, so divide both sides by 2, and x is negative 1. So that's our solution. So negative 1, 0.